This is the chapter on thermodynamics, and we already talked about the first law of thermodynamics way back in thermochemistry when we talked about enthalpy. So now it's high time that we talk about the second and third law of thermodynamics, and those are related to entropy. So we already have one formula for talking about entropy, and that was entropy S equals the Boltzmann constant times natural log of the number of microstates W. And while we're at it, we might as well convert that to delta S, a more useful variable. Boltzmann times difference in microstates, which looks like a quotient because of the natural log. Okay, so this is one way that we can talk about entropy, is using microstates. And now we're going to introduce a different way of discussing entropy, which is with heat. Specifically, reversible heat, which we're not really going to discuss in detail, but reversible heat is the maximum possible heat that can occur in a particular process, and assuming infinitesimally small steps and very high efficiency. So we have our new formula, and we also need to revisit our definitions of system and surroundings. So here's a picture that I drew back in the entropy chapter. Hot coffee, very large mug of coffee, I must say. So in this picture, the coffee was our system. That was the point of interest. And the mug, in addition to the rest of the known universe, the mug and everything else in the universe represents the surroundings. So the surroundings is not just the mug, it is everything else that is not the system. So now we're going to use these two pieces of information to dig into the second law of thermodynamics. So looking at this picture of the coffee mug, we could confidently say that the universe, in the way that we've defined it here, is the system plus the surroundings. That encompasses everything. If it isn't the system, it is the surroundings. And this relationship is true for talking about the entropy. So we could say that the change in entropy of the universe equals the change in entropy of the system plus the change in entropy of the surroundings. And so now we can use this formula that we introduced with heat over temperature, and we can introduce that into this formula. Write that a little more neatly here. So the change in entropy of the universe equals heat flow of the system over temperature of the system plus heat flow of the surroundings over the temperature of the surroundings. Okay, so there's a lot of good stuff in here. There's a lot of interesting terms we can start to substitute for. So now we're going to ask the question, how does the entropy of the universe, the change in entropy of the universe, relate to a spontaneous process? What happens to this variable if a spontaneous process occurs? So let's draw a picture of a spontaneous process that we are familiar with from earlier in the chapter, or earlier in the course, I suppose, back in the enthalpy chapter. Let's say we have a hot piece of metal in a bucket of water. So this is going to be our system, the metal, and everything else, the water and the bucket and the entire known universe is going to be the surroundings. So this is going to be hot piece of metal. The water is going to be cold. And so we can say to ourselves, if we have a spontaneous process, which direction of heat flow is going to be spontaneous? This is not a trick question. The natural thing we would expect to happen in this picture is we would expect that the heat from the hot cube would flow into the surroundings, right? That's the natural spontaneous direction. So spontaneous direction of heat flow is hot to cold. And we can assume that the temperature of the hot object is greater than the temperature of the cold object, because that's what temperature means. So now let's take the information that we've indicated on this picture of a spontaneous process, and let's try and use it to do some qualitative calculations using this formula. So what do we know about these variables based on our picture? So Q of the system. We don't know what Q of the system is, but we can decide on what the sign would be. So if the cube is our system and the heat is exiting the system, that is going to be a negative number. So I'm going to call it negative X. And Q of the surroundings is gaining heat, so that is going to be a positive number. And because I know that Q system is equal and opposite of Q surroundings, it's going to be the same value, just with the opposite sign. All right, that takes care of the numerators. So now let's look a little bit more closely at the temperature. We already specified that the hot object should have a higher temperature than the cold object. So let's say that this is going to be the larger denominator, and this one is going to be the smaller denominator. Again, we don't know how big the numbers are, but we know how they relate to each other. So now let's think about this fraction. Both of these fractions have the same numerator, but they're divided by different denominators. So if this number, if x were equal to 5, for example, if we took 5 over a large number like 100, this would be the smaller of the two fractions. So a negative smaller number. And then over here, if I had 5 divided by a smaller number, the entire fraction would be larger, like 5 over 10. So this is going to be a positive larger number. So in conclusion, if I have a positive larger number and I subtract a smaller number, I'm going to end up with some sort of a positive number for the entropy change of the universe. And that is our second law of thermodynamics. So the second law of thermodynamics says that entropy change for the universe is going to be positive for any spontaneous process. And that's important. So we'll put that in a box. So now we have a real definition for entropy, a real definition for spontaneity involving entropy. Anytime the entropy change for the universe is positive, that means that it's a spontaneous process. So now we'll move on to the third law of thermodynamics, and that one also involves entropy. So this one is going to involve the first expression for entropy, the one with the microstates. And so for the third law, we're going to ask a different question. We're going to ask, what is the minimum entropy? How ordered can we possibly make this system? What's the smallest possible number we can get? And since this formula is here to help us, we can see that this is a constant, W is our only variable, and S and W are directly proportional. So we can already conclude that it would occur, minimum entropy would occur when there is a minimum number of microstates possible. Minimum entropy, minimum number of microstates. So what exactly is the minimum number of microstates? Could we possibly have 0 microstates? No, we couldn't have 0 microstates because every particle has to exist somewhere, but we could have 1 microstate. If there is only one possible location for every particle in the system, there would only be 1 microstate. And so we talked in the previous lecture video about how to maximize entropy. Here's a flashback. And so we can use these same criteria to try and minimize entropy by looking at all the criteria on the right side. So to minimize entropy, we could include fewer particles. We could use a pure substance instead of a mixture. We could decrease the molar mass and make the particle orientation more spherical rather than more linear. We could decrease the temperature as far as possible and keep the compound in a solid phase. So if I were to draw a picture of the substance with the lowest possible entropy, I would draw a solid. The solid is the phase of matter with the lowest entropy, lower than liquids and gases. I would use a pure substance where all the dots are the same color. And I would want the vibrations to be as low as possible. So this is solid state, pure solid, pure substance. And I would want to decrease the vibrations as much as possible so there was only one possible microstate this could exist in. So I would want to decrease it to the lowest possible temperature. And what's the lowest possible temperature? Absolute zero. 0 Kelvin. So now if we go back to our formula and we finish the job, entropy is going to be Boltzmann constant times natural log of 1, the lowest number of microstates. And so that'll be Boltzmann constant times natural log of 1, which is 0. So our entropy is going to equal 0. And that's our third law of thermodynamics. It says that entropy is going to equal 0 for a pure, perfect, crystalline substance at absolute 0. And that's important, so we'll put it in a box. The question about the laws of thermodynamics actually came up in a trivia game that I played last week, so these are not worthless pieces of information. They can help you win a game someday. All right, now that we know everything about entropy that is possible to be known, including the second and third laws of thermodynamics, the last piece of information we need is about the standard change in enthalpy. Change in entropy. Gosh, those words are similar. Standard entropy. Delta S naught. So we'll put our usual asterisk like we did before. Standard values are awesome because you can find them in a reference table. We have specified a set of conditions that we like the most, that are most applicable, and folks from all over the world have measured these values so that we can look them up and use them without having to do every experiment from scratch. So the conditions for standard entropy are the same as for standard enthalpy. So it is the entropy at 1 atmosphere, technically 1 bar, but around 1 atmosphere, and 25 degrees Celsius, unless specified. Because sometimes compounds don't exist at 25 degrees Celsius in the standard state. And remember, we also have to include standard states. So this is standard entropy is for 1 mole of product formed. And it is formed from elements in their standard states. This should all sound familiar at this point, just with a different letter. Okay, so this is one familiar concept, using the standard entropy from elements in their standard states. And because the change in entropy is a state function, we can also use another trick from the enthalpy chapter, and that is products minus reactants. The change in standard enthalpy of the products times their coefficients added together, minus the standard enthalpy change for the reactants times their coefficients and added together gives us the total standard enthalpy change for a reaction. And these numbers, just in case you forgot, those are the stoichiometric coefficients, the numbers that come before each compound in the balanced equation. So now you can officially say that you know everything there is to know about entropy and everything there is to know about enthalpy. And in the next video, we will combine entropy and enthalpy into a third variable that encompasses both of them to help us definitively predict whether a reaction will be spontaneous or not.